We have lecture 62, confidence interval for the difference of means. Okay, I say here our situation is as it was with hypothesis testing when we were looking at a difference of means. We have two populations where there is no natural pairing between a member of one population and a member of the other. In the case where there is that natural pairing, we look at the mean of differences as we did in the last lecture. But here we don't have that, and we don't know the standard deviation of either population, and we don't assume that they're equal. We don't know either population mean, and what we want to do is estimate the difference between mu1 and mu2, the two population means. We want to estimate, in other words, mu1 minus mu2, and we want to get a confidence interval for that. Okay, so the things that we build, the computations we do are going to be very similar to what we've done for hypothesis testing for a difference of two means. So we take a simple random sample of size n1 from the first population and size n2 from the second population, where we make sure that both those are bigger than 30 unless we know that their respective populations are normal. And so what we need to do is compute the 100 1 minus alpha % confidence interval for mu1 minus mu2. You need the point estimate and the margin of error, and then you have everything you need. So the point estimate. It's what you would think. It's the sample mean from the first sample drawn from the first population minus the sample mean from the second sample drawn from the second population. Okay, and what's the margin of error? The margin of error here is similar to a calculation you made back when we did hypothesis testing. It's T alpha over 2, where of course alpha is our, we think of that, this is the critical value here, right? And the T, for the T distribution, and it's times the square root of S1 squared over N1 plus S2 squared over N2. So a little more complicated, you know, than it is if we're just dealing with a sample from one population. But again, you've seen that before. So what do I say here? Off to the side, let's just note stuff that I think is obvious. X1, X2 are the sample means. And I don't think I need to say that the X1 comes, I don't need to write that X1 comes from the first population, a sample from the first population, and X2 comes from the second, that's obvious. And S1, S2 are sample standard deviations. Okay, so what is our 101 minus alpha % confidence interval for mu1 minus mu2 down below there? It is just x1 bar minus x2 bar. There's our point estimate, plus or minus our E, all right? So we can also write that, of course, as x1 bar minus x2 bar minus E and x1 bar minus x2 bar plus E. There is our confidence interval. Okay, and I want to just do one example. I think this is pretty straightforward. Once you understand what all the things mean, and again, it's all familiar to you, and you need to know how to do this computation and that computation and how to put them together, you have what you need. So, next page, or I guess down below, example, let's go back to lecture 52, where we had two groups of tomato plants. One we treated with fertilizer and one we did not. We had the control group. Instead of doing a hypothesis test for the difference of means, let's just do a confidence interval estimation of what that difference is. So recall, we randomly select, this is just like the problem from before, in lecture 50, I guess it was 52. We randomly select a set of 40 tomato plants that we will not treat with the fertilizer and 50 plants that we will treat with our fertilizer. We allow the plants to grow the prescribed length of time, after which we measure the yield from each plant. In the, let's see, in the untreated sample, I guess, no, sorry, in the treated sample, we find the mean is, X1 bar is 13.9 pounds per plant with a sample standard deviation of S1 equal 3.1 pounds. In the sample that's untreated, we find a mean of X2 bar equal 12.2 pounds and a standard deviation S2 equal 2.8 pounds. All right. So because of the way I set this up, we're going to look at the confidence interval for mu1 minus mu2. So I wanted to make the first sample be the treated one where the yield gets bigger, and I wanted the second sample then to be taken from a population where it was untreated. And so that's why I was confused there for just a second, but yeah, so our first population is the treated, we're giving it the fertilizer, the second one is where it's untreated. Okay, so if mu1 would be the mean yield of all tomato plants were they to receive the fertilizer, and mu2 would be the mean yield for all plants if they were not to receive the fertilizer, so there's our two population means, then we wish to estimate mu1 minus mu2. Let's find a 95% confidence interval for mu1 minus mu2. All right, so next paragraph there is kind of our step 0. We have two samples, one from each of the above populations. Both samples are larger than 30, and we do not suspect that the standard deviations of the population are the same. And I make a little parenthetical note there that if they were the same, we could simplify some things, but it's not much of a simplification. It doesn't make things much better, so we're just going to not even worry about that ever. Okay, so we can proceed. So that was kind of step 0, all that. And step 1 then is we compute our sample means and our sample standard deviations, and we have all those. So X1 bar is 13.9. X2 bar S1 is 3.1, X2 bar is 12.2, S1 is 3.1, and S2 is 2.8. All right, well, we may as well go ahead and compute the point estimate here. So in step 1, typically if we're dealing with one population, then finding X1 bar would be our point estimate, but since we're dealing with two, our point estimate for mu1 minus mu2 is X1 bar minus X2 bar. So that's what, 13.9 minus 12.2, that's 1.7. This is pounds, right? Okay, excuse me. Step 2. Get our T alpha over 2. And I'm saying a 95% confidence interval. By now, I hope you think 5% left over. Half of that is 0.025. So I want T 0.025. And I go look that up. And where do I look? I have to look in, I don't have it. I have, let's see, N1 is 50. N1 equals 50. And N2 equals 40. So the degrees of freedom off of here would be 49, off of here would be 39. We use the lesser of the two, right? So that's our method here. So we would look under degrees of freedom 39, and for T 0.025, I get 2.023. Remember, degrees of freedom equal 39. All right, step 3 then. What is the margin of error? It's T alpha over 2. Square root of S1 squared over N1 plus S2 squared over N2. So that's 2.023 times the square root of S1 squared is 3.1 squared over N1 is 50 plus S2 is 2.8. We square that, do it over 40. And you work that all out, and what do you get? You get 1.26044. So that's a 1.26044, et cetera, et cetera. Since we've computed our statistics so far out to the nearest tenth, we'll do the same thing here. So that's 1.3. Okay. Step 4. Well, just what is the the confidence interval then. It's 1.7 point estimate plus or minus 1.3. Right, and it's a little better if we write that in interval notation. 1.7 minus 1.3 is 0.4. 1.7 plus 0.3 is 3, or let's say 3.0. Okay, there is our 95% confidence interval for mu1 minus mu2. But of course, if that's all you have, it's kind of confusing. You don't know what you have really. You need to have a conclusion that lays it all out. So let's write that one. What is the conclusion? The conclusion is we are 95% confident that the mean difference in per plant yield of, let's say between, pardon me, we'll just say between instead of. Between the fertilized plants fertilized and unfertilized plants is between 0.4 pounds and 3.0 pounds. Okay, just stating out what the confidence interval is telling us there. Yeah, so, excuse me. What's kind of nice about this, and we'll talk about this, I'll probably talk about this at a later lecture, but what is really, one thing that's nice is I have an estimate. My best estimate of how much better the yield is if I fertilize the plants is 1.7 pounds. My 95% confidence interval is between 0.4 pounds and 3.0 pounds. You notice that the lowest I go with 95% confidence is still a positive number, right? It's 0.4 pounds. So the lowest I think at a 95% confidence level, the lowest I think the fertilizer improves things by is 0.4 pounds, which maybe isn't a lot, but it is something. If my confidence interval was bigger and went down all the way to 0, then I'd have 0 inside my 95% or whatever percent confidence interval, and 0 means that there's no difference, right? So the fact that my confidence interval does not contain 0, isn't that like a hypothesis test? Hey, I really do believe there's a genuine difference here because my confidence interval doesn't even contain 0. So I have, while getting an estimate and getting a confidence interval that tells me where my difference is, I've also actually kind of performed a hypothesis test. I have good reason to believe that there really is some difference. It isn't 0. I'm far enough away from 0. I have 95% confidence. Well, actually more, because I could expand this a little. If I grew the confidence interval, I could up my confidence level. And as long as I stayed away from 0, I could say, hey, I at that level of confidence, I don't believe I got, that there's no difference, right? So I actually can perform a hypothesis test there. This is why I kind of like confidence interval building more than a hypothesis testing, because there's a hypothesis test kind of contained inside if you know how to read it correctly. And we'll talk more about that in the future, but we'll stop here for now.